Okay, so set theory. So we learned about a set. Yes, I told you that set is a primitive notion in set theory. We don't try to define it, but we understand what the meaning of that is. And then if you want to, you have to have some punctuation rules. For example, if I want to describe a set, I just show it with a capital letter, put equality sign, then I open a curly bracket, and then I list the elements of the set and separate them with a comma, and then whenever it is done, I just close them. And we also talked a little bit about finite sets, infinite sets, and then we realized what is the meaning of cardinality. For example, if I have a set, 1, 2, 5, 7, I can put anything inside, I don't know, a box or something like that. So that is a set with a little bit weird elements. They are not homogeneous. But anyway, that is not the part of the problem. You can put whatever you want to inside the set as elements, and then the cardinality of the set is the number of elements there if the set is finite. So for this case, 1, 2, 3, 4, 5, 6, the cardinality of the set is 6. But if I have an infinite set, of course the cardinality becomes infinite. Then we realize that we might have different sizes of infinities, even though that was not part of the this lesson. What we discussed about this a little bit. And then we also learned that usually we describe the elements of the set by mathematical symbols. For example, the famous example is the set of rational numbers, which is the set consisting of all x's such that, so these are the notations we use, x is equal to a fraction, but not any fraction, the fraction whose numerator is an integer belongs to set z, and then b also belongs to z, and b is not equal to 0. So we describe the elements of a set. So because the elements of this set doesn't follow any regularity or pattern, so we cannot use the dots. But for the set of n natural numbers, I can write 1, 2, 3, and then I can put some dots because this follow the same pattern. And then we learned about a concept of being a subset. Do you remember? So we say that A is a subset of another set B. A is a subset of B. What does this mean? How should we define this? When do we say that A is a subset of B?
All elements of A exist in the set.
Yes. So in other words, if I want to say, I would say for all x, if this is true that x belongs to A, then x belongs to B. So this is the mathematical way of defining this subset. Okay. The simple examples are these two, for example. A, let us take it 1 and 2, and then I would take it B, 2, 3, 5, 1. So you immediately see that A is a subset of B because all the elements in A are also in B. And then one crucial point about sets is that we don't have any order of elements. Order does not matter in a set. So if someone writes this in this way, 2 and 1, and then call this set C, then immediately we say that A and C are equal. Okay? Do you remember the properties that we discovered for this subset relation? Yes?
Every subset is a subset. Every set is a subset of itself.
Yeah, every set is a subset of itself. So if I just pick a random set, no matter what are inside, this is always true. You don't need to see what are the elements in A. You can say this is always true, and that is clear because whatever is on the in the left hand side, it is already on in the right hand side. Yes.
We also said that the empty set is a subset of every set.
Yes. So before doing the second one, we have to describe the empty set. Do you remember the empty set, which is this symbol, is denoted by this symbol? Is the set you open the curly brackets, there is nothing to put in, then you close it. So that is called the empty set. And then I told you that sometimes people get confused. I hope that you understand or you remember that this is not the empty set. So empty set is like an empty bag But if I ask you what does this, if I want to use an analogy of empty bag here, if you want to visualize it, it is a bag which inside that bag there is an empty bag. So the bag, the first bag that you open it is not empty because it includes another empty, an empty bag. So be careful. This is not equal to this one. In other words, if I say what the cardinality of empty set is 0, but what the cardinality of this set is, what is this? 1. Because it includes a thing in it, and that thing is an empty bag. So the cardinality of this. Of course, this is clear that if two sets are equal, then the cardinalities are also equal, but the other way around is not true. It might happen that I have two sets with the same cardinalities, but they are not the same. Okay, so this is why we add this one to the list. But do you remember how we, if I want to read this in words, I would say that the empty set is a subset of every set. Okay? But do you remember why that was true? In order to understand why that was true, we said that this is vacuously true. What do we mean by that? We say that, okay, when you say A is a subset of B, this means what? For all x, if x belongs to A, then x belongs to B. Now I ask you to define what do we mean by this if you say. When we say A is not a subset of B, what does this mean then?
There exists some element in B which does not belong in there.
No.
In A.
In A, which does not belong. Okay. So there exists an element x so that x belongs to A and x does not belong to B. So when I say A is not a subset of B, it means that this statement is true. Okay, can I say that the empty set is not a subset of A? This means what? This means there exists an element x which, so what I'm just comparing this with this one, whenever I see A, I put the empty set. Whenever I see B, I put the set A. So this becomes there exists, x belongs to A, but it becomes the empty set, and x does not belong to B. And so here A. So you understand that this is false. Because if you believe this is true, it means that you have to believe this statement is true. If you believe that this statement is true, it means that you are able to find an x which is in the empty set and is not in your set. But this cannot happen because you cannot find an element in the empty set. So this statement is false or true? False. This statement is the same essentially. So if this is false, this one is just its translation. So that is also false. But if this statement is false, then I have to admit that this statement, which is the negation of that one, is true. So that is the proof of the empty set being a subset of every set. Okay? There was another property, do you remember? This subset is a relation among sets, yes?
If A is a subset of B and B is a subset of C.
So, which is called the transitivity property, yes? So if A is a subset of B and B itself is a subset of another set, C, then if you want to, you can conclude that, so let me put them in a pair of, this I don't need to put, this pair of brackets I put, okay? And then I would say that A is a subset of C as well. This is called transitivity, okay? And this is not only, so you see any relation that you have, you can talk about reflexivity, transitivity, and symmetry, okay? So these are just for your information. So reflexive, a relation can be reflexive, symmetric, and transitive. These are the words that, transitive, yes. These are the words that sometimes it is good to know. This is not part of your lesson, just for extra information. If an element, if every element is in relation with itself, that relation is called reflexive. Okay? For example, if I go to the numbers, the set of numbers, and I consider the relation of equality. Okay? So is equality relation within numbers reflexive? If you see this phrase, it means that is it the case that every number equals itself? This is the meaning of being reflexive. Yes? So is equality reflexive? Is equality relation reflexive? Yes. Symmetry means if a number is related to another number, then that number is also related to the first number using the same relation. In other words, if A is equal to B, is it guaranteed that B is also equal to A? Yes, so we say equality is also symmetric. And transitive means if A is in relation with B, here my relation is equality, and B is in relation with C, again my relation is equality, is it conceivable to say that A is also equal to C? Yes. So this is reflexive, symmetric, and transitive. And of course, this is also good to know. If a relation have all these three properties, we call it an equivalence relation. Yes.
Sorry, what did you say that reflexive was?
Reflexive means that every element is in relation with itself, using that relation. So, and then this is the simplest possible equivalence relation. But equality is too restrictive. They have to be identical. Yes.
So can you do this for like addition or or subtraction, for example?
No, you have to have a relation. For example, let me ask you. This might be better. On the set of humans, for example, if I consider all humans being in a set, let me see. Friendship is a relation. Is friendship reflexive? If I am your friend, you are my friend. No, am I friend with myself? I don't know. So you can say yes or no. Okay, that is up. It is up to interpretation. But if I am your friend, you are also my friend, in principle. So this means that friendship is symmetric. But is friendship transitive? Not in general. Yes, I am your friend. You have another friend. There is no reason that I am the friend of your friend. So it is not transitive. So I don't know. For example, brotherhood. It's also a relation among humans. So is brotherhood reflexive? No. And no more. Yeah. Okay. Is brotherhood reflexive? Symmetric?
I mean, if I'm
No.
woman, if you're a girl.
If I am your brother, might be you're my sister. So that is sisterhood. Yes. So brotherhood is not symmetric. But is brotherhood transitive? If I am your brother, you are also brother to another person. In principle, I am brother to that person as well.
That person's brother.
Or no. If I am your brother, yes, I will be her or his brother. That's correct. Yes. Yes. No? Okay, so
You don't have to.
so how?
Say, I am my brother's brother. He has another father than me, and then.
Okay, so you are making things complicated. I'm talking about a standard ones. Okay, yes, of course I have to. But I mean, yes, so brotherhood. For example, similarity among triangles. Do you think similarity is an equivalence relation among triangles? What do I mean by that? Imagine you have a set. Inside the set, every triangle is an element. Now my question is that we define a relation on this set of all triangles. Is relation of being similar to is equivalence relation? When I say equivalence, it means that you need to check all those three. Let us check. Every triangle is similar to itself. That's true. if triangle 1 is similar to triangle 2, then triangle 2 is also similar to triangle 1. That's also correct, so it is symmetric. And if the triangle 1 is similar to triangle 2 is similar to triangle 3, then triangle 1 is definitely similar to triangle 3. So it means that similarity on the set of triangles is an equivalence relation. Okay? Okay. But for example, the relation of belonging to among the sets again. So being a subset was transitive. Is it symmetric, by the way?
No.
Not in general. The example is on the board, yes? This one is a subset of this one, but not the other way around. Okay? So we learned that. So it is reflexive, it is transitive, but not necessarily symmetric. So this relation is not an equivalence relation. Yes? By the way, what about this one? This is also, we learned about this. So let us consider the set of integers. Okay, now let us consider the set R. And the relation I want to define is less than. Do you think that this less than relation on the set of real numbers is reflexive?
No.
No. Because to be reflexive, it means every number should be less than itself, which is not correct. Is it symmetric? It's also not, because 1 is less than 2, but 2 is not less than 1. Is it transitive? It is, because if A is less than B and B is less than C, then A is less than C. But now let us consider this. What do you think about this? Is it reflexive now? It is reflexive. Every number is less than or equal to itself. Is it symmetric? Not necessarily again. Yes, because 1 is less than or equal to is true, but 2 less than or equal to 1 is false. So I cannot, it is not symmetric in general. Is it transitive? It is. Okay, let us say something about number theory. Okay, so let us take this Z and this relation. Do you remember A divides B? I mean, not that symbol there, division symbol. Okay, so now this symbol, which is the divisibility relation, do you think it is reflexive?
Yes.
Every element should be related to itself.
Every element
In my definition, yes. Do you remember when I was talking, I told you that in my definition, 0 divides 0 is true. Yes, because I told you how. What was my definition for A divides B? This happens if and only if there exists a Q in Z, so that what happens? B is AQ. If you take this definition, then 0 divides 0 is true. Yes, why? Because if I want to convince myself this is true, I need to be able to find at least an integer q so that when I multiply it on the left, it becomes equal to the right. So can I do this here? Yes. Any number that I choose. Even one of them is enough, but I have infinitely many choices here because the number on the right is 0, the number on the left is 0. Can I find an integer so that it works? Yes, any integer you like makes it work, okay? So if you take this definition as divisibility, and that is why this is good to have this definition. So this means that this is what now? This is reflexive. Because we didn't have any problems to say 2 divides 2, minus 5 divides minus 5. Of course, these are. The only doubtful thing is if 0 divides 0, but if you take this definition, that is also true. So I would say that yes, this is a reflexive relation. What about symmetry? Do you think it is symmetric? No, because 2 divides 6, but 6 does not divide 2. Is it transitive? If A divides B, B itself divides C, is it guaranteed that A divides C? Yes or no? We had these before, yes? And we did the example today, yes? I remember when I wanted to give a geography exam or history exam, that was very astonishing from my memory. I knew more or less very good thing before the exam. As soon as the exam was finished, I forget everything. I don't know how it happens. But of course, hopefully not for math, yes.
Divisibility is transitive.
It's transitive. Yeah, we had this before, yes? So if A divides B, what does it mean? It means that B is AQ. I'm lazy, but I should write Q belongs to Z. And B divides C, it means what? C is BQ prime. Q prime is an integer. And then what should I do? Instead of B here, I put this B here. So this means that C is AQ prime. What does this mean? This means AQ prime. But Q prime is an integer. So A times an integer is C. So this means that A divides C. Yes. So that's also transitive. Okay, but what about belonging to relation? Let us investigate that one as well. So if I am working with all sets, and then I want to talk about belonging relation. So we realize that this relation among sets is reflexive, not symmetric, but transitive. I want to answer the similar questions for this relation. Is this reflexive? If it is going to be reflexive, it means every set should belong to itself, which is not true. Okay? For example, if I write A equals to 1, if I ask you to write a set to which A belongs to, what do you write? So that is the important thing. You have to open a curly bracket, and then you can put a lot of things inside, but you have to be careful that you also need to put this inside. So for example, let me write like this. And this set is no longer that set. Okay? So this is not the case. By the way, I am just forcing you to believe this. In mathematicians, they realize this is not something that I can force you. They put an axiom to prevent this, and that is called regularity axiom. Okay, but let us assume that we are working in set theory in an intuitive baby way. You know, this set that we are talking about is naive set theory or baby set theory, but even this set theory is not even reached to baby. Okay, so it's not a baby either, but anyway. So what about this one? It is not reflexive. For example, this set does not belong to itself. Yes? To have a set that contains this as an element, you have at least 2 more curly brackets. Okay, so this is not reflexive. Is it symmetric? No. But is it transitive? If A belongs to B and B belongs to C, is it guaranteed that A belongs to C? No, yes? And I think we had this last time. So can you remember the example? Very simple example. So let me take this one to be just 1. And let me take B to be curly brackets. Inside the curly brackets, I put 1 with curly brackets. Then I am respecting this. I hope that you agree with me that A belongs to this set. Everyone agrees? Yes? Okay. And now if I want to write another C, I open a curly bracket, another curly brackets, another curly brackets, and then put 1 here. Now, do you think that I am respecting this now or not? Yes, because this is an element here. But is this an element there? No, because if I ask you, what is the cardinality of this? 1, and what is the element is 1. What is the cardinality here? 1. What is the element is this one. And if I ask you what the cardinality is there, you say 1 again, and what is the element inside is this one. Okay? So you see that A belongs to B because this is your A, and this is the only element of B, which is A itself. So this is true. This one, B belongs to C, yes, because this is B, which is here, and this is the element of C. But A does not belong to C. So you see that this relation is not transitive. So, for example, I belong to Sweden. If I consider the set of countries, So I belong to Sweden, Sweden belongs to the United Nations, but it doesn't mean that I belong to the United Nations. Okay? So you have to be a little bit careful about these things. But can you cook up an example that this becomes true? Yes, when I say something is not true, it means there exists a counterexample. It doesn't necessarily mean that in all circumstances it is false. You might be able to cook up some examples for which this is true. For example, let me take A to be 1, let me take B to be the same. But instead of C considering that one, I write it as 1 here, okay, and then I would write it like this. Yes? So A belongs to B in this case is true. B belongs to C is true because you see B here. And A belongs to C is also true because you see A here. So it is possible, but when I say it is transitive, it means that in all circumstances it should work, which is not the case in this one. Okay. And so there is one concept. Okay, do you remember there was something, I don't know if it is in the book or not, but that is good to know. In some books they have this symbol. They also can use this symbol. In old math books, they use this symbol for subset, being subset. But in the recent math books, they have invented two symbols, okay? One this and the other one this. If you see A is a subset of B in a book, which also contains this symbol at some point, then they mean A is a subset of B, but A is not equal to B. So this means that A is a subset of B and A is not equal to B. So in a book that you have this symbol, and in that book you also see this symbol, this means a little bit more than this. It tells you that not only A is a subset of B, but also not equal to it. And in that case, we say that A is a proper, I think this word is in the book, it's a proper subset of B. And this is the word I want you to know. If a set is a subset of another set but not equal to it, we call it a proper subset. Okay, one common exercise that we didn't talk in your lesson is to write all possible subsets of a set. It's a very standard problem, okay? So for example, I give you, let me write this. Example, write all subsets of the following sets. Okay, so let us start with a very simple example. So I would write A, only put 1 inside. I want to write all possible subsets. Okay? So what are the subsets of this? Yes?
Isn't it just A and the empty set?
Yes. Empty set is always there. Yes? Because we showed that the empty set is always a subset. So you can say the empty set is definitely there. Another immediate candidate is the set itself. Okay? The set itself is also a subset of itself. So what I write, I would write curly brackets 1, or if you want, you can just write its name. Can you imagine more than this? I mean, I don't want you to get confused, so don't put comma here. So let me write them in rows, okay? One subset is this, and the other subset is this. Okay? So is there any other subsets? No. So how many subsets are there? 2. Okay? The reason that I didn't put it in, because it is not in your book. There is a notion called power set. I will talk about that here for you. It is very simple. But let me give you another example. Let me call B, and let me put 2 elements within B this time. And I ask you to write down all possible subsets. This is something that you need to know. Of course, it's extremely simple. So what should I do? The first one is, again, there is no first one, last one, but let us be organized. So empty set is always a subset. And then the set itself is also always there. But is there something in between? Yes. Yes, I just open curly brackets, put A, and then close it.
And the set of B.
And then I put what? B. Can you imagine more? No. So we have 4 subsets here. Okay. Let me also talk about the power set. Power set is optional. If you don't need, you don't like it, you don't learn. The power set is a very important notion. Okay. But power set is this. So if I have, but a calligraphic P, and then you put A here. What does this mean? The power set of a set is itself a set. Okay, but what I put inside the set, the subsets of A. Okay, so these subsets that I discovered here, this is in your book. This is not in your book, but they are very related. So I open this, I put empty set, I put curly brackets 1, and then this is too far. I bring it here and close it. What I get here is called the power set of A. Okay? But power set, as I told you, is not in the book. But for example, if I say, what is the power set of B? So I open a curly brackets. I put this list as elements now. The first element is empty. I have to separate it with a comma. The second element is A. I have to separate it with a comma. The next one is B. And the next one is A and B. Whenever everything is finished, I close it with another curly bracket. This becomes a new set. That set is called the power set of my old set. Okay. Okay, let me ask you one question. What do you think will happen here? So if I put 3 here, so let me just write this set. So what are the blue sets that I will list here? This is the empty set. If you want, I can write the empty set. So what are the subsets of the empty set? Just the empty set, yes? So it becomes just the empty set. So if I ask you what is the power set, so can you tell me what is the power set of the empty set? What is the answer? I have to open 2 curly brackets, open and close, and put the blue subsets here. But I have only 1. So that is the power set of the empty set. Okay, so this is something. Let me increase the elements. Of course, in the next lesson, we will also talk about these things. I mean, when we reach to the next topic. Okay, so what do you think about, let us give number 4, C is equal to alpha, beta, and gamma. So let us list all subsets. So what are the subsets? The first one, if I want to be organized, there is no first one, second one, I told you before. But the first one is always the empty set. The last one is as big as the set itself. Yes? And then let us consider 1 element subsets. So how many 1 element subsets you can imagine? 1 with only alpha. It is, by the way, I seen this in the exam. They write alpha, they write it, the elements, they don't put curly brackets. It is extremely important to put them, otherwise you will lose that point. So you have to follow the punctuation rules. The second one is beta. The next one is gamma. Yes? A set containing only 1 element is called a singleton. Yes? I always forget about singleton, do you think? I don't know if L comes first and then let us write it like single.
Yes.
Yeah, I know single is in that way, but I don't know singleton is in that way. Anyway, so what should we do here now? Continue. These are 1 element subsets. This is 0 element subset. This is 3 element subset. I have 3 1 element subsets. But how many 2 element subsets you can imagine? 3 again. One of them is alpha and beta. The other one, alpha and gamma. And the other one, beta and gamma. So be careful. You don't write alpha and beta and alpha. No, they are the same. Order doesn't matter. So how many you can count? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so if I ask you what is the power set of that set C, so the only difference is that what do? We open a curly brackets, put this one here, alpha here, beta here, gamma here, and then alpha, beta here, alpha, gamma here, and finally beta, gamma here. No, not finally, this is finally. Alpha, beta, gamma, and then close. That's the powers. Yes. But do you see any relation for the cardinality of the power?
I was just gonna ask that, is it 2 to the power of?
Yes, it is 2. So if this is just a guess, but we will be able to prove it later. So if I ask you what is the cardinality of a power set, what is that? You see here I had 3 elements, I had 8 subsets. Here I had 1 element, 2 subsets. 2 elements, 4 subsets. 3 elements, 8 subsets. So it is clear, the pattern more or less clear. It's 2 to the power of the number of elements. So what can I write here? If I want to write a formula for you?
Power of the cardinality?
Yes, 2 to the power of cardinality A, of course, if A is finite, because otherwise it doesn't make sense. But even in higher mathematics, it can be proven that whenever you make the power set of an infinite set, it becomes an infinity of a higher order. It is not possible to make a one-to-one correspondence between an infinite set and its power set. So if I have an infinite set, the power set, of course, becomes also infinite. But this is not like even numbers and natural numbers. Both of them were infinite, but I try to convince you, no, they are of the same size. But no, when it comes to taking, this is why power sets are important, because it has been shown in the set theory that if I have an infinite set and then I construct its power set, that also becomes infinite, but it can be proven that that new infinity cannot be put into one-to-one correspondence with the old infinity. Yes?
Is there a symbol for all sets? Like
No, that is actually the Ratzlaff paradox. We do not have any set of all sets. Okay?
how do we define the domain of the power function then?
To what?
How do we define the domain of the power function then?
Because that's a set of-
No, I understand what is your concern. So no, we don't have a set of all sets. And I didn't say power set is a function. The way that you want to define it, you want to define it as a function. So in that case, yes, you need to have a domain of the set of all possible sets. Yes.
So if you take the power set of a power set, for an infinite set at least, do you get 2 higher orders of infinity? Or
Yes, you get higher orders of infinities every time.
So,
Yeah, that's exactly. So that's a good question. So let me ask you one question. For example, here, can you write this? Power set of the empty set. Okay, so power set of the empty set is on the board. And then I want to make the power set of that set. So what should I do? Yeah, I just write all the subsets. So I need to open 2 curly brackets. And what is in this? I want to wait for you, by the way. What do you write here? Yes?
Or should you write the empty set itself?
Yes. So you just write the empty set. Okay? And then
Then you write, well, the set of the empty set.
the set of the empty set. Is there anything else? No. So it is too far. So that is the power set of the power set of the empty set. Yes? Let us do one more. Power set of power set of power set of the empty set. Okay? Yeah, it's not hard, but it is good to realize. But how many? So could you anticipate there will be 2? Because power set of the empty set is contains 1 element in it. If we take that pattern for granted, the next level will be 2 to power 1, which is 2. So what will be the next level? 2 to power 2, which should be 4. So I need to open, but this is extremely important. You see, I am just exaggerating the curly brackets so that you can understand what's happening. Now, inside this, I need to write all subsets of that set. So what is all subsets? It always starts with the empty set and always ends with the set itself. The set itself, I copy and paste it here. And a little bit squeezed version. Yes? So this is the first in my hierarchy, and this one is the last one. But I might have also something in between because I learned that how many are there? 4. So there are 2 more left. Okay, so what should I write here? Yes.
The set of the empty set and the set of the empty set.
So just tell me curly brackets.
Curly brackets, empty set. And close.
Yes.
And then curly brackets, another empty set.
Like this
Yes.
and like this.
Yes.
Yes. That's good. So that is the power set of the power set of the power set of the empty set. Yes. So exactly, it's not hard, but yeah, you need to get used to it. Is that clear? But anyway, you don't need to learn power sets because it's not in the book. But the notion of subsets and writing all of them is in the book. So that is a very simple thing to do. Okay, let me test your understanding here. So if I ask you, let us go back to the book, but let us make the problem a little bit harder. So let me write this one. Oh, we are done, yes? Okay, sorry. Yeah, goodbye. We do it later.